In power systems, circuit breakers are used to switch electrical equipment and networks under normal and fault conditions. The primary function of a circuit breaker is to interrupt the flow of current, load, or short circuit by opening its contacts and thereby isolating the switched parts of the system. The design and working of a circuit breaker depend on its application and voltage rating. Molded case technology with air at atmospheric pressure is used at low voltages, whereas air blast and vacuum circuit breakers are prevalent at medium voltages. SF6 circuit breakers are normally used for high voltage systems. Disconnecting a load, interrupting a fault. Sulphur hexafluoride gas is a colorless, odorless, non-flammable, and chemically stable gas with excellent dielectric and arc quenching properties, making it ideal for use in high voltage switchgear. One of its primary applications is in SF6 circuit breakers, which are widely used in modern power systems for protecting equipment by safely interrupting high fault currents. SF6 circuit breakers are categorized into different types based on voltage level and construction, commonly dead tank, live tank, and GIS gas-insulated switchgear types. These breakers are composed of several main components: the interrupter unit, where the arc interruption takes place using high-pressure SF6 gas, the insulating stack or bushings that provide insulation and mechanical support, the mechanical operating mechanism that drives the opening and closing of contacts, typically using spring or hydraulic power, the control panel, which manages signals, interlocks, and protections, and various additional components such as gas density monitors, arc chutes, heaters, filters, and pressure relief devices. The working principle of an SF6 circuit breaker involves the use of pressurized gas to extinguish the arc. Under normal conditions, the breaker remains closed, and the SF6 gas serves as an insulating medium. During a circuit breaker opening operation, when a fault is detected, the operating mechanism separates the contacts, an arc is formed and immediately quenched by a blast of SF6 gas directed through a nozzle. Once the arc is extinguished and current reaches zero, the breaker fully opens. In a closing operation, the mechanism drives the moving contact to reconnect with the fixed contact under the protection of SF6 insulation. To ensure reliability, SF6 breakers must meet specific design requirements, including high mechanical endurance, fast operating times, low contact resistance, complete gas-tight sealing, and conformance to international standards like IEC 62271. Overall, SF6 circuit breakers offer high performance and compact design, but due to environmental concerns associated with SF6's high global warming potential, careful gas monitoring, leakage prevention, and recycling practices are essential in their usage. SF6 circuit breakers utilize sulphur hexafluoride gas as the surrounding insulating medium for extinguishing the arc established between the moving breaker contacts. It has many favorable characteristics that make it an ideal insulation candidate in modern high-voltage switchgear: high dielectric strength, about 8 to 9 times greater than air at 5 bar pressure. Electronegative in nature, i.e. catch free electrons forming heavy ions with low mobility that prevents an avalanche type of breakdown. Good thermal heat transfer capability, high ionization energy and low dissociation temperature, resulting in excellent arc extinction properties. Very high electrical conductivity at elevated temperatures, proving low arc voltage. Colorless, odorless, inert, and non-poisonous. Some of the disadvantages of SF6 gas are its high cost, its tendency to form corrosive metal fluorides during arcing, and the fact that it is a greenhouse gas. SF6 circuit breaker types. At present, SF6 circuit breakers can be classified into two major categories: dead tank enclosure at ground potential, live tank enclosure at line potential. Dead tank designs can offer greater short-circuit current breaking capability and seismic rating, but are relatively bulky, require more SF6 gas, whereas live tank designs are modular and more compact. There are also several different ways in which the electrical current and resulting arc in an SF6 circuit breaker can be interrupted. These types include double pressure, now obsolete, single pressure, also called puffer, self-blast, where arc energy supports pressure buildup in arc chamber, rotating arc rotates electrodynamically in cool background gas, and double motion technology with two moving contacts. In addition, the drive mechanism of the circuit breaker can be of the hydraulic or spring-loaded type. Construction and main components. A complete assembly of a single pressure puffer type SF6 circuit breaker consists of the following parts: interrupter unit, the separation of circuit breaker contacts, quenching of the resulting arc and interruption of current takes place in the interrupter unit. It houses two sets of contacts which are commonly called the main or normal current carrying contacts and arcing contacts. Both types of these contact sets have one stationary contact whilst the other contact is able to move. Current carriers providing connection to the external circuit breaker terminals are connected to the stationary and moving main contacts. The tips of all circuit breaker contacts are coated with a copper tungsten arc-resistant material. The main body of the interrupter, which is filled with SF6 gas, contains a moving puffer cylinder that can axially slide upward and downward along the contacts. There is one stationary piston inside the cylinder which is fixed with other stationary parts of the SF6 circuit breaker, in such a way that it cannot change its position during the movement of the cylinder. A nozzle is located at the opening of the cylinder. Main components of SF6 circuit breaker interrupter: insulating stack. The interrupter unit is vertically mounted on top of an insulating stack which is made up of a hollow insulator encapsulating the drive rod which connects the mechanical operating mechanism of the circuit breaker to the moving contacts housed within the interrupter. Depending on the voltage rating of the system, the insulating stack may be a single piece or multiple segments mechanically coupled in series. Just like any other insulator, it provides adequate line-to-ground dry arcing and creepage distance to prevent flashovers associated with transient over voltages and ambient pollution. The complete circuit breaker unit is usually fixed on a steel structure which secures it to an embedded concrete foundation. Mechanical operating mechanism: the driving apparatus provides the kinetic energy required to open and close the circuit breaker contacts. It consists of a set of opening and closing springs that are charged manually, or with the help of a small electric motor. Control panel: the control cubicle communicates between the circuit breaker mechanical operating mechanism, system protection relays and supervisory devices. It can be configured for either remote or manual operating setting. Additional components: at extra high voltage, usually 380 kV and above, due to manufacturing economics and design requirements, the SF6 circuit breaker may have notable differences in construction and may also feature additional components. Instead of a single interrupter unit, two or more interrupter units are connected in series and mounted horizontally onto the insulating stack. For such circuit breakers, grating capacitors C are connected across the interrupters to equalize the voltage across them. For transmission line switching applications, these circuit breakers may be equipped with pre-insertion resistors PIR to dampen high magnitudes of switching transient over voltages. These PIRs, normally 300 to 600 ohms, are connected in parallel with the CB main contacts. They are inserted in the circuit for a specified time interval 8 to 12 milliseconds before main breaker contacts are closed. Different configurations of SF6 circuit breaker: the external connecting terminals are fitted with grating rings to ensure that the electric field stresses at the terminal surface do not exceed corona onset. How SF6 circuit breakers work: in the normal condition, the circuit breaker contacts are closed and current flows from one contact carrier to the other via the main contacts and the sliding puffer cylinder. Circuit breaker opening operation: when the circuit breaker control panel receives an opening command to clear a fault or disconnect part of a network, it sends a signal to the trip coil of the mechanical operating mechanism, which in turn releases the latch holding the charged opening spring. As the opening spring discharges, it pulls the drive rod connected to the interrupter in a linear direction, which causes the moving contacts and puffer cylinder to move downwards. The movement of the puffer cylinder against the stationary piston leads to a decrease in the puffer cylinder's internal volume, which causes compression of the SF6 gas inside the cylinder. Due to contact overlap, gas compression starts before any contacts open. As the downward movement continues, the main contacts separate and the current commutates to the arcing contacts, which are still in the closed position due to their physically longer construction. During the course of further opening, the arcing contacts start to separate and an arc is established between them. Operation of a puffer-type SF6 circuit breaker: as the arc flows, it blocks the flow of SF6 gas through the nozzle to some extent. Thus, the gas pressure in the puffer cylinder continues to increase. When the sinusoidal current waveform approaches zero, the arc becomes relatively weak and the pressurized SF6 gas inside the puffer cylinder flows axially through nozzle over the arc length. This blast of SF6 gas removes the thermal energy in the contact gap and reduces the degree of ionization electrical conductivity such that the arc is extinguished. When the arc is interrupted, transient recovery voltage starts to appear across the contacts, the opening speed of the circuit breaker contacts should be fast enough to create an adequate contact separation distance to withstand this voltage stress. In case the contact gap's dielectric strength is lower than TRV stress, the arc will be re-established in a phenomenon which is commonly called circuit breaker reignition or restrike. Circuit breaker closing operation. During the circuit breaker closing sequence, the closing coil releases the energy of the closing spring, which causes the contacts to move towards each other, ultimately bringing them to their normal closed position. At the same time, SF6 gas is redrawn into the puffer cylinder, making the circuit breaker ready for the next operation. Whilst closing, a circuit breaker can sometimes experience an event known as pre-strike. As the contacts move towards each other during closing, the contact gap's dielectric strength decreases. At some point, the voltage stress across the contact gap exceeds its dielectric strength, thus producing a pre-strike arc which bridges the contacts. Design requirements. In addition to the general characteristics normally associated with an electrical switch, i.e. low contact resistance when closed and almost perfect insulation in open condition, a high voltage SF6 circuit breaker needs to fulfill additional design requirements. Amongst these, the most pertinent ones are briefly described below. Rated current. The current carrying parts of the circuit breaker should be able to carry the maximum anticipated load current without exceeding temperature rise. Rated short circuit breaking current. The circuit breaker should have the ability to interrupt the maximum short circuit current of the network. Typical standardized values are 25, 40, and 63 kA. Rated voltage and insulation level. The insulation of the circuit breaker externally and across the contacts should be able to withstand specified magnitudes of low frequency and transient over voltages. Restrikes. During capacitive current breaking, the probability of restrike reignition between circuit breaker contacts should be very low. Mechanical endurance. The circuit breaker should be able to undergo a large number of operations, 2,000 to 10,000, with very limited maintenance. Opening time. To achieve adequate clearance between contacts and in order to withstand TRV, a circuit breaker needs to open in extremely fast speed in the order of 40 to 60 milliseconds. Rated operating sequence. The circuit breaker is required to satisfactorily complete a specified operating sequence. For high-speed reclosing circuit breakers, a typical sequence is 0.3 seconds CO and 3 minutes CO, where O and C represent opening and closing respectively, and 0.3 seconds and 3 minutes are time delays. Switching duty. During the course of its service life, the circuit breaker should be able to successfully undertake a variety of switching interruption duties that most notably include terminal and short line faults, transformer and reactor switching, and capacitive current interruption. In terms of demands on the circuit breaker, these different types of switching duties vary the magnitude of current and TRV that a circuit breaker is required to withstand.